Hi, welcome back. We're in the last lecture where I'm just providing a course summary, reviewing the main topics and concepts that were covered throughout the course. So in this segment, I want to talk about group comparisons. So after we dealt with multiple regression, we moved to group comparisons, where I was moving basically from non-experimental research to experimental research. So if we have experimental research, say we're manipulating an independent variable, then we could be looking at just how that independent variable affects one group versus another, or one condition versus another. The simplest group comparisons we started out, were just comparing, say, a sample mean to a population mean. And we did that with a z-test or a single sample t-test. Then we spent a little bit more time on the independent t and the dependent t. So the independent t-test allowed us to compare two independent samples, and the dependent t allowed us to compare the same subjects or the same people in two different conditions, like the working memory training example where we compared them before training and after training, the same people in two conditions. Remember, the independent t had this assumption of homogeneity of variance. We tested that through the Levene's test. If it was violated, then we applied Welch's procedure to adjust the degrees of freedom, which protects us against that inflation of type 1 error that comes along with the violation of homogeneity of variance. When we moved beyond t-tests, we were into the land of ANOVA, which was like 3 lectures, I believe. We did first a one-way between groups ANOVA, which is like doing a series of independent t-tests. So different people in different groups, and we want to compare the group means. The one-way ANOVA allows us to compare as many group means as we want. So the independent t is only appropriate when we just have 2 groups. If we have more than 2 groups, then we can apply an ANOVA. And the key statistic there was the F ratio, or F tests. That's just the mean squares or variance between groups over the mean squares or variance within groups. So S with an A was subjects within groups. Remember, we also there had the homogeneity of variance assumption. We tested it with Levene's test. And the other piece of ANOVA was that we had post hoc tests. Remember, there were different kinds of procedures that we could apply to deal with this inflation of type 1 error, or inflation of probability of type 1 error, that comes along with doing multiple pairwise comparisons. There were different procedures we applied. We looked at Tukey's procedure and Bonferroni's procedure. From there, we went to a factorial ANOVA. So factorial ANOVA is where we're introducing more than one independent variable. And again, there could be multiple levels of each independent variable. The main example I used there was that driving difficulty example with driving difficulty and conversation difficulty, looking at the effects of talking on a cell phone while driving. And that introduced other kinds of hypothesis tests. So we could look at the main effects, which are equivalent to one-way ANOVAs. We could look at the key interaction effects, or do the 2 independent variables interact with one another to cause change in the dependent variable. And remember, simple effects are the effect of one independent variable at a particular level of the other independent variable. So a way to define interaction is that the simple effects of one IV change across the levels of the other. Again, we still had the homogeneity of variance assumption. We tested it with Levene's. And again, we still had to deal with post hoc tests if we were concerned with main effects that had 3 or more levels on that independent variable. From there, we went to repeated measures ANOVA, or within groups ANOVA. Remember, the key difference there is that the concept of error changes. So it's still an F ratio, which is mean squares between in the numerator, but in the denominator, the error term is different. The concept of error in a repeated measures design is inconsistent individual differences across conditions. It's not just variance across subjects, because some of that variance across subjects now could be systematic. We could attribute that to an S term for subjects. So it's the interaction of A by S, or it's the inconsistent subject effect across conditions. right? That's the concept of interaction. That's the key difference in a repeated measures ANOVA. We also had this extra assumption, the sphericity assumption, which is not just homogeneity of variance, but homogeneity of covariance. And we tested that with Mauchly's test. If it was significant, we used a correction like greenhouse geyser. Again, we dealt with post hoc tests because if we do post hoc tests, we have to protect against that possible inflation of the probability of type 1 error. Again, we did the Holm procedure and then the Bonferroni procedure to deal with that.